Welcome back, our dear students, our candidates, 2020 Senior 4. Even some of you are in Senior 3 still. This video is very important. And we believe that you are making the best use of this time when we are experiencing the lockdown due to the coronavirus disease, COVID-19. So please make sure that you watch all the episodes. I always remind you, subscribe to my channel and get all the videos that I keep uploading here and learn together with me. This is still the S4 Physics Current Electricity series. Now this is the 50th part, and I remain your host, Mr. Mande Dennis of Seroma Christian High School in Mukono. I'm privileged one more time to have you on this platform, on this channel, following and sending feedback. Some of you actually are doing exercises and you keep forwarding the solutions. Thank you very much. I'm very happy. The parents that are supporting their children, buying for them MBs, downloading these videos, you're doing something so wonderful, and may God bless you. Actually, I encourage you to get the app called TubeMate. If you are using an Android device, it can easily help you to download. You can even use any download mechanism that you know. Get these videos so that you can watch them over and over again. Don't just watch once. It's better you watch them over and over again. And actually the resolution is always better when you download as compared to watching online. I want us to dive straight into the 50th part. May God bless you as you learn together with me. By the way, remember, get a piece of paper, or you must have a book together with you, a pen, so that you can keep jotting down important informations that you may find here. The things that you may find very important, that you may keep writing them down. All right. Now, in this part, we are going to look at electrical energy and power. Electrical energy and power. Electrical energy. Remember from the definition of potential difference, the PD between 2 points in a circuit, we say that PDV is equal to the work done over the charge that is transferred. Now, when you cross multiply, the V is equal to W over Q. When you cross multiply here, you'll get that the work done will be equal to the PD times the charge. But remember, the charge is equal to IT. Q is equal to IT. So we end up with the work done being equal to the VIT. This work done is equivalent to the energy which is used or expended. The work that is done to transfer that charge is equal to the energy that is expended. So W is equal to the electrical energy expended, which we quote by E. And thus, the electrical energy is given by VIT. E is equal to VIT. Very easy to remember, VIT. VIT, that's the electrical energy. We are saying from Ohm's law, V is equal to IR, or I is equal to V over R. Now, that expression, electrical energy, E is equal to VIT, can also be written as, now just look at this. If where there is V, we put IR, or where there is I, we put V over R, we're going to end up with two expressions. Electrical energy, E is equal to I squared RT, or electrical energy, E is equal to V squared over R times T. Those are the three expressions for electrical energy. VIT, I squared RT, and V squared over RT. The SI unit of electrical energy, like all other forms of energy, is the joule. And now they may ask you to define a joule as applied to electrical energy. So remember from here, E is equal to I squared RT. This is one of the expressions. So when do you get 1 joule here? Definitely the current must be of 1 ampere. The resistor must have a resistance of 1 ohm, and the current has to flow for 1 second. So we can say a joule can be defined as the energy expended in a 1 ohm resistor when a current of 1 ampere flows through it for 1 second. On the other hand, if you use E is equal to QV, actually the fundamental one, Q, the charge times V, you can get 1 joule if the charge is 1 coulomb and the PD is of 1 volt. So you can define this as, you can define a joule as the energy required to transfer a charge of 1 coulomb between 2 points in a circuit whose PD, or when the PD between them, is 1 volt. So a joule is the energy required to transfer a charge of 1 coulomb, or a 1 coulomb of charge between 2 points in a circuit whose PD is 1 volt. Now, what is electrical power? Remember, power is a rate of transfer of energy. Remember that. So basically, electrical power is a rate at which electrical energy is converted into other forms of energy in an appliance. The SI unit of electrical power, like for power in mechanics, is the joule per second, or what you write as a watt. You may still be asked to define a watt. So what is a watt? What is a watt? Or what is a joule per second? This is the electrical energy dissipated in an appliance when 1 joule of electrical energy is converted to other forms in 1 second. Remember, this is the unit of power, a watt. So we are saying electrical energy dissipated in an appliance. When 1 joule of electrical power dissipated in an appliance when 1 joule of electrical energy is converted to other forms in 1 second. So other large units of power include the kilowatt. You've heard of this. Kilowatt, megawatt. Yes, so kilo, this K, 1 kW, 1 kilowatt. This small k means 1000. So 1 kilowatt. Whenever I find a small k, it means there is 1000 there. And mega means 1 million. So 1 million watts, 1 megawatt. Okay, electrical energy. I remember we said it has 3 formulae. We have E is equal to VIT, E is equal to I squared RT, and also E is equal to V squared over RT times T. Now, on the other hand, electrical power, all we do is just eliminate that. Remember, power is equal to energy divided by the time. So you get power is equal to VI, that means we just leave out this T. Power is equal to I squared R, we leave out this T. Power is equal to V squared over R, still we just leave out this T. Please remember, the first 3 are the expressions for electrical energy, and these 3 are also the expressions for electrical power. All these appliances that we have, at home, like you may have microphones, we have some kettles, you may have maybe a microwave gadget, you have a refrigerator, speakers, you have a TV set, and different, maybe the home theater. All these ones have ratings. They have, if you check on them, you'll find their ratings that show you their wattage, they show you the power that they use, and they show you the voltage on which they operate. They show you the frequency of the alternating currents at which they operate. Have a look at this Philips electric iron. If you check down here, you'll find that there are details that are written, where we have 50 to 60 hertz. That is the frequency of the alternating current. 220 to 240 volts, that's the voltage. Then we have 950 to 1100 watts, that's the power, the wattage. This is made in Indonesia. So many devices have this type of, actually almost every electric appliance has this kind of marks behind if you check. Let's also have a look at this simple bulb. Yes, you can see the volts. They put 160 to 240 volts, 50 to 60 hertz. It also operates on alternating current, and its power, it's 5 watts. So let's look at examples. Here we are. A bulb is labeled 12 volts, 36 watts. What does the label mean? Question 1. Question 2. What current will flow through it? Question 3, or part C. What's the resistance of that bulb? And question D. How many joules of energy does it consume in 1 hour? So we want to answer one by one. The first one says, what does this label mean? 12V, 36 watts. This expression is very simple. This here shows you the voltage of the source onto which this bulb should be connected, and this is its power. And remember, power is a rate of transfer of electrical energy into other forms of energy. So the label means that when the bulb is connected to a power source of voltage 12V, it converts electrical energy into other forms of energy, and for a bulb it will be converting it into heat and light at a rate of 30 joules per second. When this bulb is connected to a power source of 12 volts, it converts electrical energy into other forms of energy at a rate of 36 watts, or you can say at a rate of 36 joules per second. Please, this was supposed to be 36, not 30. Make that correction, please. Thank you. Okay, part B required us to get the current which flows through this bulb. Now look at this. Remember, P is equal to VI. Or VI is equal to P, just VIP. Yeah, very easy to remember. VI is equal to P. So P is equal to VI. The power, and in simple terms, I is equal to P over V. So what is our power? 36 watts. Divide by what's the voltage? 12 V. So you're going to end up with 3 amperes. Therefore, our current I is equal to 3 amperes. 3 amperes. Part C requires us to get the resistance of the bulb. Now this is still very easy. Just remember our formula. So we are saying, remember the expressions for power. Do you remember them? So you can use, look at this information that I have summarized here. The power is given, the voltage is given, the current we've just calculated at 3 amperes. So you can use any of the formulae that involve R. So remember, we say power is equal to I squared R. So you can say the R is equal to power over I squared, which is going to be, what is our power? 36 over what's our current? The current is 3, so over 3 squared, which gives you 36 over 9. And 36 over 9 will comfortably give you 4 ohms. Therefore, the resistance of the bulb is 4 ohms. On the other hand, you can use the other formula, where alternatively you can say from power is equal to V squared over R. So you realize that the power we are given is 36, should be equal to V squared, that's 12 squared over R. So the R becomes 12 squared divided by 36, which is 144 over 36, and comfortably you're going to get 4. Going to end up with 4 ohms. So either way, you still get the same answer. But this said, how many joules of energy does it consume in 1 hour? So we are supposed to calculate the electrical energy in 1 hour. So energy is basically power times time, which save time. So we have, what is our power? We have 36 times 1 hour is equal to 3,600 seconds. So I'm getting 129,600 joules. So it means that in 1 hour, this is the electrical energy that it consumes, that bulb. We have number 2. In the diagram below, we are asked to find the current that flows through the 30 ohms resistor, the power dissipated in the 30 ohms resistor, the heat produced in the 60 ohms resistor for 5 seconds. This is the diagram. So Roman 1 says, find the current that flows through the 30 ohms resistor. Now remember, current flows from the positive terminal outwards. So if this is I, it will flow and then flow through. So that the current which flows through the 40 ohms resistor is I. When it reaches this junction, it splits up into, we can call this I1, and then some will flow this side, this is I2, and then those two currents will join up again to form the I, which will proceed back to the battery. So the question says, find the current which flows through the 30 ohms resistor. The 30 ohms resistor, the power dissipated in the 30 ohms resistor, and the heat produced in the 60 ohms resistor for 5 seconds. Can we get the effective resistance here? So effective resistance R, the external resistance. By the way, here they didn't give us the internal resistance. That means it is negligible. The effective resistance will be, if you look at this kind of arrangement, realize that the 30 ohms resistor and 60 ohms resistor are in parallel. So we shall say 30 times 60 over 30 plus 60. And that combination is in series with the 40 ohms resistor, so plus 40. So you're going to end up with 20 plus 40, which will give you 60 ohms. So we found out that the total external resistance R is equal to 60 ohms. Now, can we use this to get the general current which flows through the circuit, the I? Remember, that general current will flow through the circuit, and at this junction, it will flow through even the 40 ohms resistor. When it reaches this junction, it splits up. We can call it the current which flows through the 30 ohms resistor I1, and the current which flows through the 60 ohms resistor, let us call it I2. So those two currents will then proceed and still add up here to form I, which continues back to the battery. Now, can we get I from EMF E is equal to I into R plus R. This is the total external resistance R, this one here, and this is the internal resistance. But remember, they didn't give us the internal resistance. That means it is negligible, or it's 0. So this part, we are going to end up with EMF is equal to I R. So the EMF is 6 volts, should be equal to I, the one we are looking for, times the total external resistance, which we have as 60. So I becomes 6 over 60, which gives us 1 over 10, and that is 0.1 amperes. Now, can we get the current which passes through the 30 ohms resistor? The current which passes through the 30 ohms resistor. How do you get it? Remember, if this is R1 and this is R2, You can use our formula. I1 is equal to R2 over R1 plus R2 multiplied by I. So we are saying our I1 will be equal to, what is R2? R2 is this other one, and this is R1. And the current here is I1, and the current here is what we're calling I2. So I1 is going to be 60 over the sum of the two, which is 90, times the current which comes, that's 0.1. And from your calculator, you should end up with something like 0.066 recurring, which you can round off and write as 0.0667 amperes. Now the question was, you are supposed to get the power which is dissipated in the 30 ohms resistor. So power, use the expression, power is equal to I squared R, which is going to be the current we got there. It's going to be I1 squared R1. So the power, the current we got was 0.0667. So square it. It's always better to write that in fraction, by the way, to avoid errors. You can write this as in fraction. This can be 2 over 30 amperes, which is same as 1 over 15 actually. 1 over 15 amperes. Yes. So we are saying 0.0667 squared times R1, which was 30. And so you end up with here so we are ending up with 0.133 recurring watts. Now go ahead and do the last part, which talked about I think they wanted you to get the energy. Yeah, here for the 60 ohms resistor, you can do that. I have a series of questions for us to try out. I'm just going to display them. Try them out because they involve the things that we have learned over over this series in the different parts. So please do them. You can pause and then you do those questions. Thank you very much.